All right, 7.1, exponential growth and decay. So this whole chapter here is going to be about exponential functions, logarithm, things of that nature. And the big idea that right away you can spot that something is exponential is that everything we've done before, we've had linears, which are like y equals x, or actually x to the first. We've had quadratic, y equals x squared, which were parabolas. Those were lines. Then we had our power functions. So we had things like, y equals x to the third, which kind of did something like this. And then we had y equals x to the fourth, which kind of did something like that. And we could keep going. We could do fifth, sixth, seventh, whatever. Well, today the big difference is we are going to have some sort of an equation where we have a base number, but our x is going to be up here in the exponent. All right, so that's the big difference, is our variable term is going to be up here as the power. So that's how you can kind of spot one of these people. So exponential functions are functions where the variable x is in the exponent. We normally refer to this piece right here. This is called the base. And this is the exponent. All right, and the base has got to be greater than 0. And not equal to 1, because if it's 1 to the something power, it's just going to stay 1, and it wouldn't be very interesting. So bigger than 0, but not equal to 1, so it can be fractions, it could be bigger numbers, and we'll see some examples here in a second. So let's go to this next one. It says, consider the function f of x equals 2 to the x power. Make a table and graph it. So let's just kind of get an idea of what this thing may look like. So I'm just going to treat f of x as y, and I'm going to make my table. And I'm going to start with 0, but since our grid over here, goes from positive 4 all the way to negative 4, I'm going to put 0 in the middle. I'm going to go up to positive 4, and then I'm going to go to negative 4. And let's kind of just start with 0 and see what we get. So when I put 2 to the 0 power, well, anything to the 0 power is 1. So I know that this 0.01 is on there, and it's commonly on a lot of graphs that are exponential. Not all of them, but quite a few. And then if I use 1 as the exponent, and I go 2 to the first, well, that's just 1. 2 squared is 4. Actually, I take that back. 2 to the first power is 2. 2 squared is 4. 2 to the third would be 8. And 2 to the fourth would be 16. So let's kind of get those on here. I have, this was actually supposed to be a 2. So 1 comma 2, over 2 we're up to 4, over 3 we're up to 8. And at 4 we're way off the screen. We're too far up to even put it. Well, now if we go in the negative direction, if I do 2 to the negative 1, if you remember back in algebra, how you deal with negative exponents is 2 to the negative 1 is going to be the reciprocal of 2 to the positive 1. So you basically just put a 1 on top, and you do 1 over 2 to the first power, which would be 1/2. Another way to view this as, if you look at this function, it's kind of getting chopped in half. Every time we go up, we're getting cut in half. So that's another way to kind of do it. We could kind of just keep cutting each previous term in half. So half of a half is a quarter. Half of a quarter is an eighth. Half of an eighth is a 16th. But you should see this relationship between the fourth power is 16 and the negative fourth power is 1 over 16. That relationship is going to kind of happen. So let me graph this over here. So we go to a half, we go to a quarter, and a lot of times with these things you just have to kind of approximate about where it is. So if we were to graph this, it would kind of look something like so. Whereas you move to the right, it's starting to grow at an increasing rate. Now, one thing I want to talk about is right now, this thing will never go to 0. I don't care what negative number we put as an exponent. If we keep cutting it in half, it's never going to cross 0 or even touch 0. So this line right here, it's kind of like a little force field that is not going to allow this graph to touch it or cross it. And we refer to that line as an asymptote. Usually the P's kind of silent. We usually say asymptote, but it's spelled asymptote. And basically that is a line that the graph never touches or crosses. Like I say, it's kind of like a force field. It just stops it, and it'll get closer and closer and closer. It approaches it, but it never crosses it. Whenever you see this base of 2 here, this sometimes is known as the doubling function. So just kind of a little vocab, something that might pop up later, but that's the doubling function. 3 would be a tripling function, so on and so forth. So that's exponential functions. Now exponential growth kind of has its own variation of that. So exponential growth is oftentimes written as y equals a to the 1 plus r to the t or to the x. I'm going to put t in here because it makes a little bit more sense for these problems. But in the graphing calculator, I put it as x. But what these represent is the y is our final value when all is said and done. This a number, this is going to be the initial value, okay, or the starting amount. And in order for it to be exponential growth, a has to be greater than 0. We have to start with something. We can't start with a negative amount. R is going to be our growth rate. So for instance, if our growth rate was 12%, we would be plugging in for R 0.12. You always want to use a decimal for your percentage. And just to kind of be careful, so other percentages, let's say it was 7%. Remember, that would be 0.07. You have to put a 0 in front of single-digit percents. If it was something like, I don't know, 3.5%, if we get something like that in a problem, it's going to be 0.03. That would be 3%. And then you just put a 5 on the end. So I'm just kind of showing you some possibilities. If it grows by like 125%, then that would be 1.25 for my R. So you're always just dividing the percent by 100. That's kind of the rule. Divide the percent by 100. And then T is how many times? It's usually minutes, seconds, hours, days, years, who knows? Depends on the problem. All right, let's get into this example. An island is populated with 1,000 rabbits. So this is our starting amount. We grow, at 8% every year. And why the 1 is there is because if you start with 1, that means you're just staying the same. 1,000 times 1 means we didn't lose any, we didn't gain any, so you're kind of in balance. But we're growing, so we're going to add to 1 8% every year. And it says, how many rabbits will there be in 15 years? So I'm going to be compounding 15 times. So here's going to be my equation. And to find the final amount, I basically just punch this in the calculator. 1,000 times parenthesis 1.08 to the 15th power. And it looks like it's about 3,172 rabbits will be after the 15 years. All right, next problem. Let's go on down. Number 2, a collector purchases a rare guitar in the year 2000 for $12,000. So that's my starting amount. It increased its value on average 14% a year. So that's going to be 1.14. We don't know how many years, so this is what we're looking for. We're looking for our X or our time. And we want to know, when is it going to be worth 60,000? Well, later on in this chapter, we're going to solve this using logarithms. But for right now, we are going to graph the function. We're going to graph this function right here. And we're going to look at the table to give us an idea. And we're looking for 60,000. So let's go ahead and let's pull up our graphing calculator. Let's fire this joker up. And, oh, it's already in here. So we have $12,000 times 1.14 to the x power. And instead of going on my graph, because that's going to be a little bit harder to interpret, we're going to go to our table. I'm going to set my table back to where it probably would normally be. Must have did this one in class. So if I check the table out, well, I can see that the price is going up every year. And I'm looking for, when did it get to $60,000? So right there, somewhere at year 12, it was at 57, and year 13, it was at 65. So I could answer this question, and I could say, well, sometimes or somewhere between 12 and 13 years. Now, I didn't really tell you how nitty-gritty to get to it. If I wanted to, and I wanted to get down to the nearest tenth or the nearest hundredth, I'll show you how to do that. Basically, I could just hit second table set. And let's start at 12 because we know it's right after that. And let's go by, I don't know, let's get really in there, 0.01. So now when I go to my table, I could find out a little bit closer, where does that 60 end up being at? Right there. It looks like somewhere between 1228 and 1229. So if I really need to hone in and really zoom in where I'm at, I can adjust the table and I could be like, hey, we're really fine-tuning it now and getting somewhere between that time frame. So it all depends on the question, what they're asking. All right, let's move on down. Exponential decay. So exponential decay, very similar, but they're going to be in this format. Y equals A times 1. And the only difference is it's going to be minus the rate. All right? And we still have our time. So everything is the same. It's just for decay, we subtract. So let's do an example here. It says the value of a truck bought new. So when we bought it brand new, it was 48 grand. It decreases 9%. So we decrease 9% every year. So there would be my function. And on an SAT or something, they would probably simplify that. And they would actually clean that parenthesis up. And they would put it as 0.91, which is another way of saying we're preserving 91% of our value every year. We're losing 9, we're keeping 91. So it's kind of the same thing, just from different areas. Part A says, what is the estimated value in owning it for 3.5 years? So what I'm going to do is I'm going to just plug in 3.5 for x and see what we get. So let's pull up our graphing calculator again. And let's just quit out of this and go to our normal calculator. And we're like, all right, we had $48,000 times 0.91 raised to the, and we wanted to know 3.5 years. So it looks like 35,505.32. So 35,505, and if we wanted to get right down to the pennies, that would be the value after 3.5 years. Now it says graph the function to estimate how long it'll take before it's worth, and I think that's $10,000, but let's just slide, yep, $10,000. So I need to go to the graph and kind of play the same game I played earlier. So let's clear this out. Let's go 48 G's, parenthesis, 0.91, parentheses, to the, when you don't know what year it is, you're going to put an X in there. And hit enter, lock it in. And my table's all wonky, so let's go to table set. And let's go 0, and we'll go by ones. And let's go second table, see what we get. So 48,000, I'm looking for 10,000. Getting close, getting close. All right, somewhere between 16 and 17 years. And we'll just call it good enough for that one since I already showed you on the one before. But if you hold on to that guitar, 16, 17 years, or not guitar, truck. If you hold on to that truck for 16, 17 years, it'll be worth 10 grand. Maybe. I don't know. Seems like a lot to me, but who knows? Let's go down, see what we got next. Bacteria. So on this one, it says a sample contains 500 counts of bacteria. It's our start. We triple every 20 minutes. Now be careful. Don't just jam the 20 in right here because this is kind of important. You have a couple different things to consider. Every 20 minutes, but for 4 hours. So what you kind of have to ask yourself is you have to say, how many times will it compound? All right, if it's every 20 minutes, that would be 3 times per hour. It's 20 minutes, 20 minutes, 20 minutes would be 60 minutes. So 3 times an hour times 4 hours. So it's actually going to happen 12 times. So I'm going to put the number 12 in here. So I'm going to go to my calculator. I'm not going to pull it up on the screen for time's sake. But 500, 3 to the 12th, just regular calculator. I'm not doing graphing or anything. It's a giant number. 265,720,500. So there's going to be over 265 million bacteria basically in 4 hours if it triples every 20 minutes. All right, so that's exponential growth right there, buddy. All right, moving it right down, this magic piggy bank. So magic piggy bank doubles the amount of money every day. If you put a penny in to start, so we put a penny into start, 0.01, and it doubles. So I'm going to use a 2 for my growth factor. It doubles. How much money will there be in there after 30 days? So start basically a penny a day and you double it for 30 days. And it's almost unbelievable when you put this in your calculator. But doubling is like, it gets out of hand pretty quickly. 0.01, 30 to the, or not 30, 2 should be in parentheses. 0.01, parentheses 2, parentheses, upside down V, aka the caret symbol, to the 30th. Holy smokes. It is 1073741,824. So you will have over $10 million in the magic piggy bank if you double every day for 30 days. Pretty mind-boggling. All right, so that's a quick little lesson on exponential growth, exponential decay. Hopefully this can get you through the practice. See you.